In this video here, we're going to take a look at rectangular hyperbola. Now let's say then that we slice a cone here in such a way that it slices both halves. If we do this, we obtain a curve called a hyperbola. And this diagram here then shows a hyperbola. So we slice a cone here such that it slices both halves. And as we can see then, right, we obtain this curve here called a hyperbola. So for this chapter here on conic sections 1, we're only going to consider a specific type of hyperbola called a rectangular hyperbola. So this curve then has two asymptotes which meet at right angles. So for the next chapter on conic sections 2, we do start to look at hyperbola in more detail, but for this chapter here on conic sections 1, we're only concerned about rectangular hyperbola. So let's introduce then rectangular hyperbola more formally. So to get us started here then, as we can see, right, we have this diagram here, and this diagram shows a curve, and the curve is a rectangular hyperbola with the Cartesian equation xy is equal to c squared, where c is just a positive constant. Now this curve also has parametric equations, and they're given as follows. So x is equal to ct, and y is equal to c over t, where t belongs to the set of real numbers, and t cannot equal 0. The curve also has asymptotes at x equals 0 and y equals 0. So in other words, the x-axis and the y-axis. And then finally here, a general point P on the curve has coordinates of x, y, or ct and c over t. Obviously, this is just dependent on whether we're working in Cartesian form or parametric form. Okay. So there we have it in terms of an introduction here to rectangular hyperbola. We don't need too much more, so I think the best way to work through rectangular hyperbola here is to just take a look at one practice question. So let's have a go then at this practice question here. So for this question then, as we can see here, right, we have the rectangular hyperbola h, which has the following Cartesian equation. We're then told that the line L with this given equation here intersects the curve at the points P and Q. So for the first part of this question, then part A, all we want to do here is find the coordinates of P and Q. So nothing too challenging here, just to get us started. So for the first part then, part A here, the first thing that I need to do is take this equation here for the line L and rearrange this and make either x the subject or y the subject. Now, it doesn't matter which of these two you make the subject, but generally speaking, right, we want to make the easier choice, which in this case would be y, right? Because if I just add y to both sides, we've made y the subject. So in that case then, if I add y to both sides here, y is equal to 2x minus 4. Okay. And what I'm going to do now is take this rearranged form here then for y. So y is equal to 2x minus 4. And I'm going to substitute that into this Cartesian equation here then for the rectangular hyperbola h. So once we do that, we get x times by y here, which is 2x minus 4. So I get x times 2x minus 4. So this is xy, and xy is equal to 16. So this is equal to 16. To expand the left-hand side here then, I'm going to get x times 2x, that's 2x squared. X times minus 4, I get minus 4x there. And now we've got this 16 here, but I want to set this equation equal to 0. So what I'm going to do then, if I do it all in one line, then I'm going to subtract 16 off both sides as well. So I get 2x squared minus 4x minus 16 here is equal to 0. Okay. So clearly we can divide through by 2 here. So if we do that, we get x squared minus 2x minus 8 is equal to 0. Okay. Now the next thing here then is we'd hope that this factorizes. And the good news is then this does indeed factorize. So what we get here then is x minus 4. We get x minus 4 and x plus 2. Okay. This is equal to 0. So what we get here then is two x solutions. So I find x equal to 4. So x equals 4 and x equals minus 2. Okay. But what we also need here then is the respective y solution, right? So going back to this equation here then, or this equation, it doesn't matter, it's completely up to you. Y is equal to 2 lots of x minus 4. So for example then, when x equals 4, let's do that up here. So when x equals 4, y is equal to 2 lots of 4. So that's 8 minus 4. And we get 4 there. Okay. And when x equals minus 2 here, so when x equals minus 2, what we get here then for y is 2 lots of minus 2. So that's minus 4. Minus 4. We get minus 8 there. Okay. So in that case then, let's say that p here is minus 2 minus 8. Therefore, p is minus 2 minus 8. And q is the other point here of 4, 4. Okay. So truthfully, it doesn't actually matter which one we assign as p and which one we assign as q. I like to work from left to right though. So the first x coordinate here, I assign as p, and then the next x coordinate I assign as q. But it doesn't actually matter, right? So p here is minus 2 minus 8, and q is 4, 4. So that gives us the solution to part A. So now for part B then, just as a follow-on here, it says find the equation of the perpendicular bisector of PQ in the form ax plus by plus c equals 0, where a, b, and c are integers to be found. So the first thing that we need here then is the midpoint of PQ. Okay, so for the midpoint here of PQ, let's just write this down. So midpoint of PQ here. Well, nice and straightforward here, right? We just average the x coordinates, average the y coordinates. So 4 plus minus 2, or minus 2 plus 4. It doesn't matter which way we do this. So minus 2 plus 4. We then divide that by 2, right? We're just taking the average of the x coordinates. Do the same here then with the y coordinates. So minus 8 plus 4. Again, over 2 here. And if we evaluate this here then, what you should find is we get 1 and minus 2 here. Okay, so we get 1 and minus 2 there. So this here then is the midpoint of PQ. We also need the gradient of PQ, right? So we need the gradient of PQ. The gradient of PQ here, nice and straightforward, right? So m is equal to, so I'm going to do 4 minus minus 8. So 4 minus minus 8 here. And that's all over 4 minus minus 2 here. Like so. So in this case here, we get 4 plus 8, which is 12, all over 4 plus 2, which is 6. We get 12 over 6 there, which gives us 2. Now just be careful here, right? Because we want the perpendicular bisector. So what I need here then is the negative reciprocal of this gradient. Okay. So gradient of perpendicular bisector. So as we just said then, this would be the negative reciprocal of this here. So this is 2 over 1, flip it and times it by minus 1. So what we get then for the gradient of the perpendicular bisector is minus a half. Okay, so we're pretty much done now. So what we're going to do here is use the formula then for the equation of a straight line. So y minus y1 is equal to m times x minus x1. Okay, so x1 here is this point here. So that's 1. Y1 would be this point here, so minus 2. Okay, so we get y minus minus 2, so that's just the same as y plus 2, is equal to m. So this is the value of m that we use here, the gradient of the perpendicular bisector, as opposed to the gradient of PQ. Okay, so just be careful with that. So minus a half times by x minus x1, which is 1. So the next thing that I'm going to do here then is times through by 2. So this will just ensure that we have integer coefficients. Okay, so we get 2y plus 4. So 2y plus 4 is equal to, so I then get minus 1 times by x, that's minus x there. Then minus 1 times minus 1, we get plus 1 there. Okay, and then finally, once in this form here, so ax plus by plus c equals 0. So what I'm going to do here is add x to both sides and subtract 1 off both sides. So if we do that here, then what we get to finish with is x plus 2y. And then finally, we have 4 minus 1, giving us plus 3 there. Okay, this is all equal to 0. And notice at this point here, then we have it in the required form. So all that's left to do here then is just identify A, B, and C. So in that case then, A is simply 1, B is 2, and C is 3. So nice and straightforward there. So A equals 1, B equals 2, and then finally here, C equals 3. Okay. And there we have it. So that gives us the solution to part B and the solution to, I would say, the very last question here, but we did just have the one question for this video. But there we have it. So that brings us to the end then of this video here on rectangular hyperbola.